In this video, we're going to have a quick look at MIPS as well as some of the key features that we're going to be using as this course goes on. So, what is MIPS? Well, MIPS is an assembly language that uses a 32-bit architecture. In fact, you can get 64-bit alternatives to MIPS, but we're going to be using 32 bits for the sake of ease of use and having less to worry about. MIPS has a very simple and clean design. That is because MIPS uses what's called a reduced instruction set, favouring shorter, simpler instructions that execute quickly over more complicated instructions that take more time to execute but do more at once. MIPS was introduced in 1985 and is still used today. If you've seen any of the other lectures, then you'll know that MIPS is mainly used for embedded systems nowadays, but has in the past been used for famous machines like the PlayStation 2, the PlayStation 1 or the Nintendo 64. To program MIPS though, we're going to be using a simulator called Mars. Mars has got a very nice interface. It provides a lot of helpful features for programming in MIPS and should be very easy for you all to install. So let's have a look at some MIPS code. You can see that it's not the most user-friendly to read, though it is human readable. So this is a lot to confront you with at first. But let's break it down and have a look at the main structure of MIPS code. So first we have the labels. Now labels are useful for not only saying what your code does. For example, in this greatest common divisor algorithm, we have the greatest common divisor label, which shows us the main implementation of the algorithm section. And this also allows you to jump between areas of your code, which is going to become very useful for you later on, because MIPS code is unstructured. Now what that means is when you write out 100 lines of code, MIPS will just execute one line after another. It doesn't move around unless you force it to. So if you have 100 lines, it will just go line 1, line 2, line 3, line 4, line 6, so and so on. But if you use labels, then you can jump between labels of your code, allowing you to actually build algorithms in the code, which you might not otherwise be able to do. So after the labels, what have we got? Well, we've got the instructions. Now, you'll notice that some of the names are not that user-friendly. They do all have an expanded name in the MIPS summary sheet, which is provided on the My Place page. But we have a lot of instructions, so we have things like loading to registers, or we have addition, subtraction, multiplication, we have the MIPS equivalent of if statements, and the MIPS equivalents of XORs, negation, and that sort of thing. So we've got a lot of instructions, but they're all very low level, and you can find them all in the MIPS summary sheet along with an explanation of what they do. Next we have the operands, and now you'll notice that some of these have a $sign, and that's because they are registers. So A0 is a register, A1 is a register, V0, A1, A0, all of these are registers. Now some of them have specific purposes, we'll get onto that in a minute, but these operands are what the instruction takes to execute. So for example, addition takes 3 things. It takes registers to store at and 2 registers to add together. You can see here that the BEQ instruction takes 2 registers and a label, but the operands can be registers, constants, addresses, or labels. And again, if you look at the MIPS summary sheet, you can see what each instruction takes and what it does with them. Now finally, we have comments. Now in other programming languages, we all have a tendency, I know I'm guilty of it, to write less comments than we should. But I cannot stress to you how important it is that you write comments for your MIPS code, because it is going to be incredibly difficult for me to read them if you don't put comments in there, preferably at each line, so that it's easy to follow the actual idea of your code rather than the implementation. And it will make my marking a lot easier, and it will make your marks more accurate if you do put comments in there. So I'm going to be stressing this every single time I ask you to submit code. Every time I ask you to write code, you're going to be writing comments. Okay, so let's have a look at how we would do some registers in MIPS. So the ones in the little box, the bold box, these are the ones that we're going to be using mainly in this course. We might get onto some of the other ones outside of that, but we don't really need to worry about that, nor do we really need to worry about the numbers. We just need to worry about the names and the conventions for which they're used. So all registers store a 32-bit of information, so 1 word is stored at each register. Some registers have a specific purpose. For example, $0 or just the 0 register has a value of constant 0 in there, and that's quite handy for a lot of things, but that's an important one to know, the constant 0. V0 and V1 are quite important registers because they hold return values. Now, what they do, they perform what we call system calls. So that means you store a particular value in V0, and then you perform a system call and it will execute something for you. Now that might sound complicated, but that can be something as simple as printing an integer or printing a string, something like that. But we'll see how to do that in practice when we get onto the Mars simulator. So this is just a rough overview of all of them. You don't need to understand all of them immediately because things like the stack pointer, return address will become useful later on. Things like A0 to A3, they're function arguments. You can use them for temporary storage as long as you're not using subroutines. The temporary values, they're useful for storing intermediate results if you're doing calculations. You'll also notice there's a column there called preserved, and that means whether or not the register's values are preserved across subroutine calls or function calls. So you don't need to know about that just yet. That is something we will be getting onto in the future, but I'll make sure to explain that when we need to understand it. For the moment, you can refer back to this part of this video to see which of these are reserved and what the conventional usage is for them. So now let's have a look at some simple arithmetic using MIPS. So a key idea, and this is something that's going to be tricky for you all, it's tricky for me, is assembly code has no variables. So unlike in Java where we just say, oh, integer x, we're going to use that, we can't do that here. We're more restricted in what we can do. We only have registers and memory locations to use. Now they will kind of fulfill the role of variables, but there's important distinctions between the two. So when you write your high-level code in Java and you say something like a is equal to 5, then the compiler has to map that variable a to a register or a memory location so that when it can actually be executed and used at some point. So it might say a is equal to 5 and then compile that down to register T0, set that value equal to 5. Okay, so in MIPS we also need to have the data in registers for arithmetic operations. So there are some slight exceptions to this, but you do need to make sure that all of the data that you want to manipulate is in a register before you start adding and subtracting from it. And we'll see some exceptions to that later on, but this is something you need to be aware of. So let's have a look at some basic code. So I'm sure none of you would blink about writing this in Java, saying, oh, a is equal to 42, b is equal to this, and then c is equal to a plus b, c is equal to c minus 987. I'm sure that would be trivial. In MIPS we need to do a little bit more work, or a little bit more thinking. This is how we would do it in MIPS. So load immediate, what does this instruction do? You can see it saying load immediate t1 comma 42, and what this means is load immediate takes a register and a hard value and assigns that register to be equal to that value. So it says give me a register and a value and I'll put that value in the register for you. So what that's saying is T1 is going to be set to be equal to 42 using the load immediate instruction, and that's equivalent to saying a is equal to 42 in Java, Python, whatever. And then the same for load immediate T2 1001. Then we have the add instruction. So you'll notice that we're adding two things together, but the add instruction gets 3 operands. So why is that? Well, that's because the first operand that it gets, T3, is the storage location. So that says store in T3 the sum of T1 and T2, or in other words, the register T3 will be set equal to the value of T1 plus T2. So you can see here you have to think about where you're going to store the result of your calculations before you or while you perform them, whereas in Java it'd be easy just to make a variable and say that's where it's going to be stored. Okay, and subtraction, you can see down here. What's quite interesting is you can use the same register twice in an instruction. So this is saying T3 is going to be equal to T3 minus 987. So you can notice here that subtract is taking a hard-coded value. Now there are immediate ones, so you like load immediate and add immediate, you can sometimes get round storing a value before you use it, and this is one example of that, but you still need to have the storage register, and one of those values must also be something that's stored in a register. Okay, so that's everything I'd like to go over today. In the next video we'll be looking at how we do some simple arithmetic in Mars, and how we convert some basic Java code into assembly code. I hope this was useful for you. If you have any questions about anything we covered in the video, please do feel free to get in touch. Thanks.